In this presentation, we'll be discussing a case study as part of the CESBA-MED project, which is co-financed by the European Region Development Fund, where we'll be considering the University of Malta as a case study. So we will start with the urban scale part, which considered the whole University of Malta. The first part of the study was a data analysis. The University of Malta is situated in Msida, which is a central part of Malta, and it is surrounded by a number of main roads, as one can see. So this is a view of the campus, another part of the campus. So the data required, which is entered in the SN tool urban scale, consists of the areas, gross and site footprint, together with the transport facilities, the economic structure and values. So this concerns costs, employment and land values, energy usage, so electrical energy, thermal energy, primary energy demand, renewables, and also energy recycling, atmospheric emissions, greenhouse gases, non-renewable resources, water, solid waste, liquid waste, environmental aspects such as the discharge of groundwater, light pollution, air quality, noise, wind, green zones, ecological diversity, as well as social aspects, considering aspects such as safety and accessibility, traffic and mobility, communication services, public and private facilities, local food, management and community involvement, society, culture and heritage. These factors are measured by a number of KPIs. In this case, there are in all 19 KPIs, of which 14 KPIs are ready, 2 KPIs were considered as non-relevant, and 3 KPIs are still pending. Then there are also a number of indicators. The total number of indicators is 178, of which 74 are non-relevant, 39 are still pending, and the actual number of indicators carried out is 65. So, as regards areas, the University of Malta consists of a total area of 27 hectares, of which the surface area of ecological and agricultural land is 7.54 hectares, and pedestrian walkway areas are represented by 3.2 hectares. So here we can see a site plan of the University of Malta with the different faculties, institutes and centers, and we can see the different types of land usage. So the University of Malta buildings areas consists of a number of buildings, including the ICT building, which will be considered as a building scale later on, and then medicine and surgery, chemistry, IT services, engineering, Dar Giuseppe Pizarra, Maths and Physics, SLT. So these are the different faculties or buildings that constitute the University of Malta, of which the built-up area would be 26919 meters squared. In each building we have considered the number of floors, the volume for each building, as well as the ground floor area, the total ground floor area of each building. So the total ground floor area is computed as the area of that building times the number of floors. This data is taken from EPC certificates. We have then considered also the green areas in the university, which are represented by the shaded green areas here, and the walkways and pedestrian areas, which consist of pedestrian pathways, as well as piazzas. And they are represented again in this site plan over this slide. Proximity of transport. So we have two main sites where there are bus stops, and a circle was drawn to consider the coverage of that transport mechanism, and in order to evaluate how much of the university area these transport sites covered. Allocation of parking. The parking areas are designated by the blue shade over here, and in all we can see that there are 8 car parks, as well as the ring road, which is at the circumference of the university. As one can see, this total area has to cater for the administrative staff, the academic staff, students, which in total is 198 persons. So the student population is 11,500, and the staff, which consists of academic and non-academics, is 2,500. And over here we can see the growth of the university population in terms of gender, as well as in terms of academic and non-academic, as a function of the number of years considered from 1998 up to 2014. The value of land, which was taken from the National Statistics Office, the property price index, where we can see that on average the land value has increased by 5% each year, and in fact in the recent years this has even gone higher. The aim of this indicator is to assess the increase of the cost of land with regards to the increase of cost of living, and this is assessed over a 5-year period. So, as one of the factors for the economy, we will consider the employment rate, which is divided here according to the age group. And we can see that in this age group considered, we have 73% employment rate for the males and 63% employment rate for females. We can see that the males, 92% are employed in the age group 25 to 34. The main aim of this indicator is to calculate the number of people in the labor force compared to the number of working age people and express the result as a percentage. This indicator is needed to assess the labor market status, the economic development, and the citizens' quality of life. Energy. So C1 considers the non-renewable energy, so this would be the final thermal energy consumption for building operations. So we have data on the thermal energy consumption for 4 buildings close to each other at the University of Malta, and we can divide this energy by the useful area of the buildings in order to get a value which is 16 kilowatt hour per meter squared. Then we can also calculate the total energy consumption for buildings. So for the same 4 buildings which have VRF systems, it is 64.2 kilowatt hours per meter squared. So that would be the energy per area usage, per useful area. And university-wide, this value goes up to 103.2 kilowatt hours per meter squared. The lower value for the 4 buildings is where there are the VRF systems installed. Renewable and decarbonized energy. So this, we consider here the share of the renewable energy on site on total primary energy consumption for building operations. We compute the ratio of on-site renewable energy consumption to the total primary energy consumption, and in this case we get 6.9%. And in the second case we compute the share of the electrical energy generation from on-site renewable resources, mainly PV panels, on final energy consumption. The share of renewable energy on the final energy consumption expressed as a percentage in this case is 16.4%. Atmospheric emissions, so greenhouse gases, emissions from energy used for all purposes of the building operations. In this case, in Malta, there is just one power station, which is the Enemalta power station, and therefore the GEG emissions is equal to that of the power station. This result is obviously proportioned according to the energy used. The result in this case is 5,120 tons, which in terms of kilograms per meter squared would result in 76.5 kilograms per meter squared of greenhouse gases. Non-renewables, water usage. So in this case we consider the existing water network, the reuse of grey water, reuse of rainwater, reuse of stormwater. So here we have again the positioning of the University of Malta, which is surrounded by two valleys. Again, this is a plan of the University of Malta where we can see the networks, the main supply network, the water supply out of water tank, the water supply to the water tank, rainwater, and we can also note on the main supply the positions of the gate valves. This plan shows the sewage system for the University of Malta, and this plan shows the water reservoirs. So there are a number of water reservoirs which are designated by the blue shades, as well as one water tower which is designated by the orange shade. As part of renewables, non-renewables, we also consider the availability of public municipal water supply, reuse of rainwater in non-residential buildings, reuse of stormwater, consumption of potable water for non-residential building systems, solid waste and recycling collection points, separate collection and disposal of solid waste and recycling, solid waste from construction and demolition projects retained in the area for reuse or recycling. So as regards of environment, we have a number of indicators to consider. Construction activities, day and light noise, recharge of groundwater and green roofs, tree coverage, air quality, efficiency of public transport, and biodiversity. So we will consider the impact of construction activities on natural features, impact of construction activities on landscaping, soil stability and erosion, recharge of groundwater through permeable paving and or landscaping, changes in biodiversity, impact of local building user population on peak load capacity of the public transport system, impact of private vehicles used by the local population on peak load capacity of the local road system, ambient daytime noise conditions, ambient nighttime noise conditions. So in this case we have the green zones and recreation areas availability, accessibility to the same areas, the density of these areas, tree coverage for shade and management of local ambient temperatures, green roofs, ecological diversity in the area. Here we can consider the recharge mechanisms for the groundwater. So in this case one has to consider the different surface conditions such as greenstones, limestone tiling and gravel. As regards noise, we have used this instrument and we have measured noise in 3 sites, which one is the Portakabin car park 3, the other one is the IT services building, and the other one is the quadrangle. And here we took different measurements at different times for the 3 sites. So these measurements are represented in the table below at different time intervals. So this is the position of the porta cabins, which is one of the sites considered for noise analysis. This is the position of the IT services building, which was again considered for the noise analysis. And this is the quadrangle, which again was considered for noise analysis. Then as social indicators, we have the following indicators: safety for physically disabled persons, proximity of key human service, local food, bicycle parking facilities, performance of the PT, which is the public transport. So in this case we considered the proximity of key public human services. These include shops, health centers, education centers, and this parameter, it's calculated by estimating the percentage of the population which is within 800 meters walking distance from these facilities. In this particular case, it was found that 100% of the population is within this 800 meters walking distance from these services. Result. Bicycle parking facilities, there are 74 parking spaces, the population is 14,000, so this is a percentage of 0.53%. So in this case the preliminary results were analyzed with the SN tool. So in this case we consider the scales for the social aspects, the economy, the energy, the atmospheric emissions, non-renewable resources, environment. It is to be noted that 0 is considered as an acceptable practice, while 5 is considered as the best practice. These factors were weighted, and in fact we can see here the active weights which were used in this case, and when we do this weighting we get a total score of 1.88, which is just above the acceptable practice. So we will now consider the building tool, which is the IT building University of Malta, at the University of Malta. In this case we use the SB tool, building scale tool. So we have to consider site regeneration and development, energy and resource consumption, environmental loadings, indoor environmental quality, service quality, environment, cost and economic aspects. So this is the ICT building which was considered, which is a relatively new building at the University of Malta campus. Here we can see the location. It's in this case it's at the right part, bottom part of the university campus, and it is very close to the main road. So the building is relatively new, and in fact it consists of double glazed windows, fair faced concrete, copper screen, tombac roof, as well as a tombac finish. Here are other photos of the building being considered, where we can see the usage of the different materials. And here we can see the access via the pedestrian pathway and the elevation from the west side. So the ICT faculty has underground parking facility as well, some bicycle shelters in the same parking lot. Well, these are the areas of the ICT faculty. So we can see the pedestrian area, the actual internal area, the vegetation area, as well as the total land area. So in this case we can see that the internal area of one floor is 3000 meters squared, total land area is 8800 meters squared, vegetation area 4600 meters squared, the non-vegetation area is 963 meters squared. Environmental loadings. The global warming potential was computed as 41 kilogram of carbon dioxide per square meter. The impact on access to daylight or solar energy potential of access of adjacent property is 0%. That is because the university height is low compared to other, and it doesn't impact on the light access of other adjacent buildings. The degree of atmospheric light pollution caused by projection of exterior lighting systems is also low, and this is just 5%. Total volatile organic compound concentration, it was measured using these sensors which are fixed at walls, and it was found that in the indoor this was 1470 parts per million. Outside VOCs was measured to be 3300 parts per million. Again, if we look at carbon dioxide, we see that the indoor is 447 parts per million, while the outdoor is 476 parts per million. The high level of TVOC on the outside is probably because the faculty is situated very near to the main road, where there is a high level of traffic density. So a survey was carried out for the users of the building, and it was scaled using the Likert scaling. Here we considered thermal comfort, safety in case of fire and smoke, whether there was any case of flooding, safety during normal operation, satisfaction with the control of the lighting, and satisfaction with the control of heating and ventilation. We can see that since this is a closed building, ventilation satisfaction is not that good. So service quality, risk to occupants and facilities from fire, we get a result of 3.5 out of 5. Flooding, it's high, so we have 4 out of 5. Personal security, it's good, 5 out of 5. Functionality of layout, it's good, 4 out of 5. External access and unloading facilities, it's also good, 5 out of 5. Spatial efficiency, we have 61%. Volumetric efficiency, 56.57%. Degree of local control of lighting, 4 out of 5. degree of personal control of technical systems by occupants, it's 2.5 out of 5. Provision of public open space compatible with local cultural values, it's 2 out of 5. Impact of the design on existing landscapes, there is very little impact, so that is 0 out of 5. Use of traditional local materials and techniques, this is very low because, as I said, it's a quite modern building and it uses modern materials, so it's just 10%. So these are the results input in the SB tool with this course. So again, we have considered site regeneration, development, urban design and infrastructure, energy and resource consumption, environmental loadings, indoor environmental quality, service quality, social, culture and perceptual aspects, cost and economic aspects. We have given active weightings for these as are shown in this table, and the projected total score when we do this weighting is 2.78%, which is just below the good practice threshold. So, CESBA toolkit, an overview of the toolkit. So the toolkit, there is the generic framework, and as inputs here we have the criteria and the indicators. It can be used both on the urban scale and on the building scale. Then there is the assessment method as an input. Then criteria selection, benchmark setup, weights, assignments. So these have to be carried out in the context of the usage of this tool, which in this case will be Malta. And from the results we get the analysis, which is carried out both on the urban scale and on the building scale. On the urban scale we have the SN tool, on the building scale we have the SB tool. How does this tool work? Decide whether the indicator is relevant or not. So in some indicators will not be relevant for the local context. Read the assessment method and work out the ratio or percentage. Then there are two tools, the GFU tool and the SN tool. GFU tool will set benchmarks that are linked, so work on one sheet and open the other. The SN tool, then we open the SN tool and insert the worked out ratio percentage, and the program gives weightings to each and every indicator. So we have file A, which is the GFU max values. These give the weights which are input to the SN tool max, and where we have the context data, the target and benchmark in criteria B, and for every indicator we have the actual result and the limit range, and then we compute the results. Thank you for your attention.